Okay, welcome to Wednesday morning, second week of school. We're jumping into limits, and this is going to cover basically sections 2.2 and 2.4 from your book. I sort of join them together because it makes more sense to me that way. Okay, let's recall from the past. A piecewise function has the form, so we go f of x equals some brackets here, and then we list pieces. So each one of these is its own little function, and with it there's a domain that goes with it. And you can have as many pieces as you want. In fact, some functions have infinite pieces, like the wave function. We generally do 2 or 3 pieces, maybe 4. And this is just meant to be a little recollection of things from the past. And what you do is you take each piece and graph it separately. So this guy is different from this. And you put them all on the same set of axes. So for example, consider the piecewise function here. It's got 3 pieces. The first piece is a parabola, and its domain is minus infinity to 0. The second piece is a line, and its domain is 0 to infinity, non-inclusive. And then we have the point 2 at x equal 0. So 3 pieces. And we're going to graph these. We're going to graph this function on the same set of axes because it's a function. Okay, there's x, there's y. I'm going to put 1, 2, 3. 1, 2, 3, 4. Minus 1, minus 2, minus 3, minus 4, minus 1, minus 2, minus 3. All right, so we've labeled our axes. And now we're going to graph in 3 parts here. Piece 1 here is a parabola. Its vertex is at minus 2. The right-hand endpoint, even though it's undefined, is when you plug in 0 and you get 4. But it's an open circle because we're not including 0 in the domain, this first domain here. So I have this piece, and then I have this parabola here. So we've graphed piece 1. Piece 2 is a line, and it's from 0 to infinity. And so at 0 we have 1 with an open circle, and then we have x-intercept at 1, and so there's the line minus x plus 1. And then at 0 we have the point 2. So now we've graphed this piecewise function, and we want to examine what happens or what's going on at 0, right? So what happens to f of x as x gets close to 0 from the left? Okay, let's look at this. So as we're coming along here from minus infinity, x is at minus 3, it's at minus 2, it's at minus 1, minus a half, minus a third, blah, 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 minus 1/1000, and then it gets, as x gets close to 0, f of x gets close to 4. So as x approaches 0 from the left, f of x approaches 4. Even though it never gets there, it gets to 3.999 repeating forever. Okay. And so what happens as x approaches 0 from the right? Well, from the right, it's coming along this line. X is at 1, 1.5, 1, 1/2, 1/3, 1/4, 1 millionth, and so it gets infinitely close to 1. So f of x approaches 1 from the right. But what is f of 0? F of 0 is 2. So we say that as x approaches 0 from the left, f of x goes to 4. So 4 is its limit. Right? Think of 4 as a roof for the function. The function gets infinitely close to this 4, but it's bounded above by it. And as x approaches 0 from the right, f of x approaches 1. And so 1 is its limit. So 1 is its limit. There's no apostrophe there. Okay. Okay. All right, so here we go. Let's make this formal. So putting this in calc terms, using the notation, what we say is we say the lim, as x approaches 0 from the left, that's a superscript, of f of x is 4. And the limit as x approaches 0 from the right of f of x is 1. And this is called the left-hand limit. As x approaches 0. And this is the right-hand limit as x approaches 0. Now, I want you to do a guided practice problem and sketch this graph and turn off the video so you can do this. And then, turn it back on and I'll have answers for you. So here's a guided practice. I'm going to make a fun little function here. Fun little function here. Let's see here. I need 1, 2, 3. Lots of graphing in this class. Okay, let's put the function in red so it stands out here. So the first piece coming from the left is going to have an endpoint at -1, 1 here. And then I'm just going to make a cool cusp function. So it comes up like this and then takes off south and goes like that. So there's the first piece. And then down here at -1, -2, we have a closed circle. And then an open circle at 1 there, so we have this little line chunk there. That's the second piece, and then the third piece starts up here at 3, at 1, and goes off to infinity completely flat. So it's the constant function, f of x equals 3. And your task, your mission, is to, to find these 8 values. So what's the limit as x approaches -1 from the left of f of x? What's the limit as x approaches minus 1 from the right of f of x? What's the limit as x approaches positive 1 from the left? What's the limit as x approaches positive 1 from the right? There's 4, so 5. What is f of minus 1? And 6, what's f of 1? And 7, what's the limit as x approaches 2 from the right of f of x? And 8, what's the limit as x approaches 2 from the left of f of x? Okay, so find these 8 and then check them with my answers here. So okay, so let's do this. As x approaches minus 1 from the left, we're on this function, and x goes to 1. And as x approaches minus 1 from the right, we're on this leg, and f of x is minus 2. As x approaches 1 from the left, we're also on this leg where we're going the other direction because we're going left to right. That's 0. And then as x approaches 1 from the right, we're on this guy, and that limiting value was 3. F of minus 1 is minus 2. It's right here. F of 1 is 3. It's right there. And now we're going to look at 2, right? So, okay, here's 2 comma 3. And just because the function is defined there, so what's the limit as x approaches from the right? It's 3. And what's the limit as x approaches from the left? It's also 3. They're equal. And f of 2 equals 3. This combination will come back in 2.5 as a very good friend of ours. Okay, so let's make this formal. So definition. The limit of f of x approaching some arbitrary value x naught from the left of f of x equals L is called the left-hand limit. As x approaches x naught from the left. It's called the left-hand limit. Similarly, the limit as x approaches x naught from the right of f of x, I'm going to let that be m, is called the right-hand limit. As x approaches x naught from the right. Okay. And now for another definition. If L equals m, in other words, if the left-hand limit equals the right-hand limit, we call this the two-sided limit, or just the limit. Right, the limit should be in caps. Right? If L equals m, we call this the two-sided limit, and write right, but there's no plus or minus there because they're both equal to each other. So going back up to this guided practice for a second. So here's L in this game, and here's M. So what you could say here is number 9. The limit as x approaches 2 of f of x equals 3, and that's the two-sided limit because the left one equals the right one. Okay. Okay, let's do an example here. Let's go black. Okay. So we're going to compute this limit algebraically and geometrically. So let's compute the two-sided limit as x approaches. The limit as x approaches 1 of x squared plus x minus 2 over x squared minus x. So this is a rational function. Okay. Now when you take limits, and we'll talk more about this on Thursday, but when you take limits, the first thing you want to do is just plug the limiting value in. And if you get a number, you're done. But if you don't, you got work to do. So in this case, we have 1 squared plus 1 minus 2 over 1 squared minus 1. That's 0 over 0. This is very bad because it's not 0. It's called an indeterminate form. It could turn out to be a number. When you reduce it, it could be a lot of things. It could be infinity. It could be it does not exist. It's impossible to determine right now. That's why it's indeterminate, and we'll talk about this a lot in chapter 2.6. Okay, so here's where the algebra comes in. If you factor the top, you get, what do you get? You get x plus 2 times x minus 1, and then the bottom you get x times x minus 1. Okay, so these cancel. So even though 1 is not in the domain, we're left with this limit. And that's 3. When you plug in 1, you get 1 plus 2 over 1, and that's 3. So the limit exists, right? So the limit as x approaches 1 of this function is 3. But r of 1 does not exist. So there's a hole there. Or what we call a removable discontinuity. So let's graph this thing to get the geometric limit stuff going here, okay? And tomorrow night, Thursday night, in the algebra co-requisite, we will have a big chunk of time talking about these rational functions and how to graph them. Okay. So we're graphing this function. Call this r of x. Okay. Since the denominator is x equals 0, we have a vertical asymptote at 0. So hopefully this looks familiar. Since the degrees of the polynomials in the rational function are equal, you look at the leading coefficients, and x over x is 1, so there's a horizontal asymptote at 1. The numerator equals 0 at where x equal minus 2 here. And so we know, because of the pigeonhole principle, basically, we got to stay inside these two asymptotes. So I have this on the left, and on the right it must be this, because if it was the other leg, there would be a 0 there. So at 0 we have, so x equals 0 is a vertical asymptote. We also know that at 1, 3 there's a hole, because f of 1 is undefined. It's not quite in the right spot there. So at 1, 3. And that's what this thing looks like. And so here's your limit. It's too fat. Here's your limit here. Limit as x approaches 1 is 3, but f of 1 is undefined. Okay. So I'm going to give you a guided practice problem just like this to do before a meeting with me. Okay, so you're going to compute algebraically and geometrically the limit as t approaches minus 1 of t squared plus 3t plus 2 over t squared minus t minus 2. So I'm using t instead of x. And you're just going to mimic what I just did here. And then I'll see you in a minute.